Okay, in this video, let's go back to the velocity time graph and let's find out a way that we can use this graph to figure out some more valuable information about the motion of an object. So if we just read this velocity time graph, this object has a small positive velocity. It slows down to 0. It goes backwards a little bit in the negative velocity, slows back down, and then accelerates in the positive direction for a while until it slows back down. So it undergoes some dramatic changes in velocity over the course of this graph. Now let's say for a minute we want to look at two different times. Time 1 and time 2. And first we can notice that at time 1 and at time 2 the velocity changes, right? It changes, it increases. So we can go over here and say that at time 1 it has a velocity v1, and at time 2 it has a velocity that we'll call v2. So one can suppose, based on this graph, that somewhere in between t1 and t2 and in between v1 and v2 there's some average velocity, and because this is almost a straight line, it's a little slight curve, but you could suppose that somewhere right about here in the middle is the average velocity between times t1 and t2 of the object that's plotted in this motion. Now, well, how does that help us? Well, we've learned before that average velocity is related to the change in position of an object. So we've already learned that if I want to know the average velocity of something, I need to know its change in position over the time interval that goes by. Now, if we do a little rearranging here of this formula to get delta x by itself, so we're going to multiply both sides by delta t, we get that the change in position, or displacement, if you forgot that term, we haven't used it in a few videos, the displacement of an object is equal to its average, sorry, I'm writing x here, why am I writing x? Not delta x, v average, times the time interval that goes by. Okay, well, let's go back to the graph, see if we can make a connection here. What I'm going to do is I'm going to draw a little box here. Okay, I'm going to hash it out like so. And let's say I were to tell you to find the area of this box. Well, from t1 to t2, this is my time interval, my delta t, and the height of my box is my v average. So in this case, the area of this box would be my v average times my delta t, area of the box. And let's say this t1 is 4 seconds, let's say t1 is 10 seconds, and let's say v average is 5 meters per second. Then I could actually calculate this area pretty easily. I would be finding the area of a rectangle. So delta t in this case would be 6, and v average would be 5. So 5 meters per second times 6 seconds, which gives me 30, and then my seconds cancel 30 meters, which corresponds to the displacement. So if I know the average velocity and the time interval by finding the area of that rectangle, I find the displacement over that period of time. Now I'm going to make another claim, which is going to be a little hard to back up, but you can take my word for it for now. I'm going to hatch out this area under the curve. And what I want you to notice is this little portion of my rectangle is about equivalent to this little portion under the curve here. So if I were to take this and slide it over here, you can kind of see how these two numbers are actually the same, or would be the same value. So really, what I'm saying is the area under a VT curve is equal to the area of the box with my average velocity times my delta t. Now, I can't prove this to you yet. For those of you in pre-calc, this is something that is fundamental to calculus, and we're getting into the idea of integrals. So for now, you can take my word on it that the integral of this function for this between these two time periods would be the area under that curve. In the cases that we're going to use, we're looking at simpler models where we could find the area of the box knowing the V average and knowing the delta t. So the area under curve is the area of the box, which is my delta x, or the displacement of the object during that time interval. So this is a really important thing to pause and note down. When we have a velocity time graph, the area between the velocity time graph and the v equals 0 axis, or the x-axis typically when you plot v and t, is equal to the displacement of that object between those two times. So we can find displacement from the area under a velocity time graph. Furthermore, if we have an area between two times that is positive or above the x-axis in the positive v territory, that's corresponding to a positive displacement. And if we have one below, between a certain time interval like this, that corresponds to a negative displacement. So moving further away in position, moving back in position towards your origin. But when you're talking about distances from a graph, distances are always positive. So you find the area, and that just means you're moving during that time period. So if you're finding distance from that, you want to keep it as always positive. Okay, let's do a little example here. Oops, let me zoom back out. So what I have here is a velocity time graph for an object in motion. So what we want to calculate here is during certain intervals, what was the displacement of the object and what was the distance. I'll add distance on there as well. So let's look at it in terms of different time segments. So my time interval here is 1 second every mark. So from 0 to 2 seconds, here's 2. What I want to do is identify and isolate the area under that curve. So in this case, my width is 2 seconds. My height is 3 meters per second. So my delta x from 0 to 2 is my v times my delta t. In this case, v is constant. So it's my 3 meters per second times 2 seconds, which gives me 6 meters. Okay. Now, my distance in this case, also 6 meters. Right? Always positive. Okay, what about from 2 till 5? Now, from 2 till 5, my velocity is decreasing, so it's not staying constant. But what I do have is a triangle. And you guys know from math, you can take the area, or you can find the area of a triangle, 1/2 base times height. So in this case, oops, I'm going to do it equal here. I'm going to do 1/2 times my base, which is my time. I go from 2 to 5 seconds, so that's 3. And my height is also 3 again. So 1/2, 3 times 3, which will be 4.5 meters. Now from 2 to 5, the distance I traveled, also 4.5 meters. Now from 5 to 8 seconds, what's my delta x? All right, well now, I'm going to break this into 3 different segments. I have a triangle, I have a rectangle here, and another triangle. And these 2 triangles happen to be the same. So they're 1 second wide, and they're, what do I got? 3. I got to stand up to see. Well, let's say 4. Let's say this is -4. It's hard to read that a little bit. So I'm going to add my 3 sections together. 1, 2, 3. So the area from 5 to 8 will be 1/2 1 times -4 plus 1 times -4, and then plus again 1/2 1 times -4. So in this case I have -2 -4 -2. So my displacement, delta x, is a -8. But if I'm looking at distance in that region, it would be 8 meters, right? Because I'm only worried about absolute value of displacement, not actual displacement itself. So how about from 0 to 8 now? So 0 to 8, so these were hashed out together. I'm looking at this whole entire region. From here all the way over here and so forth. What's my delta x? What's my overall distance traveled? Well, to find delta x, I'm going to just sum up my delta x's in the previous region. So I had 6 meters, and then another 4.5 meters, but then a -8 meters. Don't forget your units, Mr. H. So 10.5 minus 8, I get positive 2.5 meters is my displacement. But distance-wise, remember everything's positive. 6 plus 4.5 plus 8 would give me 18.5 meters. Okay? So area under the curve gives you your displacement, can give you your distance as well. Now I want to give you guys a little bit of practice for the rest of this. I want you guys to find displacement and distance traveled from intervals 8 to 10 seconds, 10 to 11, 11 to 12, and then finally overall from 8 to 12. So go ahead and pause the video, solve those out. Okay, here's your solutions. All right, from 8 to 10, my displacement is 6 meters. I have 2 seconds here times 3 meters per second. Sorry, 2 seconds. So this is 6 meters. Here, 1/2 times 3 times 1, which is 1.5 meters, and then this is a -1.5 meters. So my overall, these cancel out. My displacement is 6 meters. Let's go distance now. Okay, I didn't write that down. Distance, the same here, the same here. These are my D's. Positive 1.5 for the last one, and then 1.5 plus 1.5, 3 plus 6, 9 for the overall. And that's finding displacement and distance from a velocity time graph.